So our next speaker is Professor Derek Krepski from the University of Manitoba. His topic today is bundle gerbes and Lie-2 algebras in two-plectic geometry. Let's welcome the speaker.
Thank you, Janet. Thank you very much for the opportunity to speak. I'll just say quickly the work today that I'll talk to you about is parts of it are joint with a former postdoc, Jennifer Vaughn, and parts of it are I guess current work with PhD student Dinamo Junbuna. Okay, so the plan for the talk today is to essentially work through the title, I guess. So we'll first start talking about bundle gerbes. I'll sort of review what those are, and then we will go over, I guess, a quick review of Lie-2 algebras, and then we'll kind of bring these two together when we talk about bundle gerbes, symmetries, and in the context of two-plectic geometry. Okay. All right, so maybe to motivate the discussion on bundle gerbes, we'll kind of recall this sequence of classifications, I guess, and maybe a quick disclaimer: if you see a manifold or a map, you should assume that it's a smooth manifold and a smooth map, and so on. So okay, so recall that cohomology classes in H1, you can think of these as homotopy classes of maps from your smooth manifold into the circle, S1. And similarly, cohomology classes in degree 2, you can view them as isomorphism classes of principal S1 bundles over your manifold. And then the question, of course, is what do you do for degree 3? And so, well, one of the things you can do is you can use S1 bundle gerbes, which are the things that we'll define next. Okay. So, and so of course there are different models, different sort of geometric objects you could choose instead of bundle gerbes, but this is what we'll talk about today. So before giving you the definition, I'll just maybe motivate the definition with an example, and we'll sort of abstract the essential elements of the example, and then write down the definition. So I'll start with some data, and then from that data we will construct a bundle gerbe, and it's called a lifting gerbe. Okay, so the data that we start with is the central extension of Lie groups, central extension by S1, and a principal G bundle. Okay, and so this gerbe has to do with trying to lift the structure group of the principal bundle from G to H, but we're not sort of gonna talk about that in any specific detail, just to give you a sense for why it's called the lifting gerbe. Okay, so so given this data, we're gonna now construct a gerbe. So here goes. So we'll start by looking at the fiber product of X with itself. So remember this, you want to think of as just pairs of points that lie in the same fiber. And because this is a principal G bundle, well, these 2 points are related by an element of G. So you can act, say, on G, act on X by G and get Y. And so over this fiber product, over the set of points in the same fiber, we will cook up the space P. And so P will be the set of triples X, Y, H. X and Y lie in the same fiber of our principal G bundle, and H is now a group element in the group H that sits over this this group element G that connects X and Y. Okay, so this is some pullback construction, and so what can we say about this particular construction? Well, some of the features are that so the base of this principle. So I guess I didn't say this, but this, if you think about this, just back up a little bit. If you think about this space P, of course, because we started with the central S1 extension, there is an S1's worth of choices for the H's that map to the G, right? So it's not too hard to convince yourself that this map P here is in fact a principal S1 bundle sitting over the fiber product. Now the fiber product itself is a Lie groupoid, so it's an example of a Lie groupoid. We just heard about these in the previous talk by Dan. And so here's the groupoid product. We multiply two pairs of points in the fiber product, and of course you need this the y's here to match up, the second coordinate and the first coordinate to match up. And so what we'd like to do then is realize that on P there's a similar groupoid product, and in this case you essentially keep the product from the Lie groupoid product from the fiber product and just multiply the two elements of H. Okay. So so far we have a principal bundle over the fiber product, and we've got this groupoid structure on P. So we have this S1 bundle, and because we have this groupoid structure, it preserves on P, which of course clearly preserves or is compatible with the groupoid structure on the base on this fiber product. So this turns this P, this principal bundle, in fact, into a Lie groupoid morphism. And if you think about the way that the elements of the circle act on P, well, it's compatible with everything here, because, for example, you know, I could act by an element of S1, which is just left translation, say by an element of S1 on the H or on any one of the H's here, and then of course I could do that on the left or the right and get the same thing. And this of course follows because S1 is central, so it commutes with the elements of H. All right, so these are the sort of basic properties of this particular example that we would like to abstract. So let's now give the definition. So an S1 bundle gerbe over a manifold consists of, so now we're going to start with just a surjective submersion over our manifold. So no need to be a principal G bundle anymore. And with our surjective submersion, we'll also have some Lie groupoid morphism as shown here. Okay, so this groupoid morphism P that sits, say, over the fiber product space. So in particular, we have this groupoid structure already on P. And this map P from P to the fiber product has to be an S1 bundle. And the S1 action has to be compatible with the groupoid multiplication. Okay, so that's sort of quickly what an S1 bundle gerbe is. And I guess we'll denote these guys either by so typically we'll just refer to the groupoid P as the S1 bundle gerbe, but if we kind of want to remember that it sits over M, we'll maybe denote it this way with you know, P goes to the fiber product and then over to X. Okay. So let's just look at a quick example. In fact, this example is pretty close to one of the examples we saw in the previous talk. So let's take X to be the disjoint union of open sets of a cover of our manifold. And so how do things kind of pan out here? Well, X, the fiber product then will just be the disjoint union of the intersections, UI intersect UJ. And so now what we'd like to do is find some principal S1 bundle that sits over this guy. But because we chose a good cover, of course, may as well choose a trivial bundle. So something like disjoint union of the UI intersect UJ times S1. And now the only thing left to describe would be the Lie groupoid product. So the product structure on this S1 bundle. So we could essentially take the naive product, which is just to say very much like what we did before, just multiply the two factors, the Z and W, but we can actually twist it now by this by some function Gij, which will be defined on, so I guess a collection of functions defined on these triple intersections as has values in S1. So of course, you can't just choose Gij to be anything. You need to this needs to be a Lie groupoid multiplication, and it turns out that the associativity of the multiplication forces these Gijks, in fact, to define a cocycle cocycle with values in S1, a 2 cocycle, and so you get, in fact, that these GIJKs represent a degree 2 cohomology class with values in S1, which is, of course, naturally isomorphic to the degree 3 cohomology of M with integer coefficients. And so that's kind of how, how these guys, or these particular examples anyway, it's easy to see that they model the cohomology classes in degree 3. Okay, so so we also have notion of connection and curvature for these bundle gerbes. So suppose we have a bundle gerbe. Connection then is going to be a connection form gamma on our S1 bundle P, but it has to be what's called a multiplicative connection. So multiplicative here means that, roughly speaking, it's compatible with the groupoid structure. Or if you like, if you pull back by the groupoid multiplication, it's the same as pulling back by the 2 projection maps. And we can wrap this condition up into, say, just a matter of notation, I guess, wrapping it up into this one equality delta gamma equals 0. So delta here sort of referring to what you might call like a simplicial differential of the underlying simplicial manifold of the groupoid. But in any case, delta gamma, you just want to think of as being delta gamma equals 0. You want to think of as being this equality here. So that's a connection on our bundle gerbe. So we also have the notion of a curving. So curving for a connection gamma. This is going to be a 2 form on X, and it's going to be a 2 form such that delta B is d gamma. So again, here the delta in this case, because the so this delta kind of lives on X, this will just be source pullback minus target pullback. But again, you might want to think of this as sort of roughly a compatibility with the groupoid structure. And so that it equals d gamma is really saying that say this curving B is related to, but it's not the same thing, but related to the curvature of the connection P, or the connection gamma on P. Okay. And then finally, if you have both a connection and a curving, it's not hard to see that if you look at the exterior derivative of B, so if you look at dB, it's so the delta of it is 0, and that turns out to mean that dB is in fact basic. In other words, it comes from a cohomology class or a form on M. Okay, so there's a unique form, a 3 form on M that pulls back by the surjective submersion to dB. And so this 3 form chi here, this would be what's called the curvature, or 3 curvature, if you want to emphasize it's in degree 3. And sort of just like the story with curvature classes on S1 bundles, this not hard to see that this curvature class is this 3 curvature is closed, and we get a Durham cohomology class in degree 3. It's sort of completely analogous to curvature and for S1 bundles in degree 2. Okay, and there it is. It's the 3 curvature. All right, so so one thing that we'll make use of a little bit down the road is so-called gauge transformations. So if you have a bundle gerbe with connection gamma, you can use a 2 form on M to kind of define what some would call a gauge transformation, so that we're not doing anything to the actual bundle gerbe, just kind of gauging the connection data. And so you can push B around or translate it by tau, and then the result, of course, would be that the 3 curvature gets moved by d tau. Okay, but we'll come back to that a bit later. Okay, so so we've talked a little bit about bundle gerbes. Now we'll move over to Lie 2 algebras. So and so this time we'll just sort of give the definition. The idea with Lie 2 algebras that if you haven't seen these before, you may want to think of this as kind of a weakening of the condition of a Lie algebra. Okay, so here's the definition. So Lie 2 algebra is going to be just a chain complex with just the two terms. So a two-term chain complex. So it's just a pair of vector spaces in a linear map, but the language of chain complexes will be convenient for us to describe the other properties. So we'll call it a two-term chain complex, and it's equipped with a bracket, so a skew-symmetric chain map. And this bracket doesn't satisfy the Jacobi identity, as say it would be the case in a Lie algebra, except its failure to satisfy the Jacobi identity now is measured by some skew-symmetric chain homotopy J. Okay, so we have the bracket just like we would in a Lie algebra, but there's no Jacobi identity. And this J here, sometimes we'll call it the Jacobiator. And of course, we need some sort of compatibility, or maybe coherence is a better word, between this Jacobiator and the bracket on, say, fourfold elements. So say if you have an X, Y, Z, and a W, and you think about how you can position the brackets, there ought to be some sort of compatibility there. All right. So okay, we can talk about morphisms of Lie 2 algebras. So if you have two of these Lie 2 algebras, a morphism will then be a map, so a chain map, because we have our two-term chain complexes. And again, we don't require this map to preserve brackets on the nose, but rather that the sort of f of a bracket and the bracket of the f's are just homotopic. So you have this chain homotopy that's part of the structure of the map or morphism of Lie 2 algebras. And just like you would with chain complexes, so of course you have chain complexes, chain maps, and then chain homotopies. Oh yeah, of course, I forgot to say that you need some compatibility, just like before. You need some compatibility between the chain map F and the chain homotopy that measures the failure of F to preserve brackets, and the various Jacobiators both on V and W. Okay, and so because we're sort of saying things in terms of chain maps, we naturally have two morphisms, or in this case, just chain homotopies. But again, you need some sort of compatibility with all the pre-existing data. So we won't really make use of this too heavily, but just to know that Lie algebras then form a two category. So we have our objects, morphisms, and two morphisms. Okay, now, so we introduced Lie 2 algebras, and it's going to be useful for us, well, in what follows, to use a sort of generalized morphism of Lie 2 algebras. And there are a few flavors of these, and the one we'll pick is known as a butterfly. So Nuhi's, due to Nuhi's butterflies. So here we go. So a butterfly then of Lie 2 algebras is going to be some vector space that kind of sits in between the two Lie 2 algebras, equipped with a bracket and various structure maps. Okay, so here's our vector space that sits between the two Lie 2 algebras, and you have maps coming in and coming out. Of course, this is called a butterfly, I guess, for obvious reasons. And we require all sorts of conditions here. So in particular, the triangles or the wings of the butterfly have to commute. We also, so just up to now, I guess there was sort of no real direction in the map from V to W. And the way we will tell the direction is by requiring this diagonal sequence from W1 to E to V0 to be short exact, okay? And the other diagonal sequence will just require to be a complex, so it's no exactness assumption there. And then, of course, that would tell you the direction that your map goes from V to W. All right. Okay, so there's more compatibility conditions. So rho and sigma, these guys are supposed to preserve the brackets. So we have brackets defined everywhere, and so rho and sigma preserve. And then, of course, there's also a compatibility of the brackets with the maps K and lambda as well. And finally, of course, there should be some sort of Jacobiator type compatibility. And if you were to write, say, the Jacobi identity on E, or at least the sum of the A bracket with B bracket with C summed over cyclic permutations, this ought to be related to the Jacobi identities on V and W. Okay, so all this to say is that there is a notion of another notion of morphism now for Lie-2 algebras, and one can, so given say an ordinary morphism of Lie-2 algebras, one can cook up a butterfly in a pretty natural way, and the nice thing about these butterflies is that so, and again, we have a two categories. So you have morphisms of butterflies just being linear maps between the bodies of the butterfly, between the E and say an E prime. It's compatible with all the structures, and we get a two category. But the reason why we would introduce the butterflies is that now quasi-isomorphisms, so if you look at the quasi-isomorphisms at the butterflies that you get from those, it turns out that both diagonal maps both diagonal sequences in the butterfly are short exact. And so we can just quickly kind of invert the butterfly, if you like, just by flipping along the y-axis, and we get a nice, well, we have a two category in which the quasi-isomorphisms are inverted as maps. Okay, so sort of similar story, in fact, to the previous talk where we were talking about localizing the category of Lie group boys. Okay, and of course, quasi-isomorphism here just means isomorphism on homology in our chain complexes. Okay, so we'll make use of four examples of Lie-2 algebras in this talk. So let's just sort of go over these, and then we'll sort of start bringing things together in the last section. So this first example, I think, is due to Christopher Rogers. So this is given a closed three form on a manifold, or I guess you could think of a two-plectic manifold where chi is also non-degenerate in some sense, but we don't need that particularly right now. So given a closed three form on a manifold, we can form the Poisson Lie algebra of observables, and so it's some two-term chain complex. Here it is. So in degree 1, it's just smooth functions on M, and in degree 0, well, we have pairs vector field in a one form that satisfy this equality here, and this might remind you, if you're familiar with the symplectic geometry. Well, we'd say in two-plectic geometry that the vector field U is Hamiltonian with Hamiltonian one form alpha. So sort of one step down. If we were talking about a two form chi, and alpha was a function, you would say that U is the Hamiltonian vector field for the function alpha. So this is the same equality, but now your Hamiltonian functions turn into Hamiltonian forms. Okay, so there's our two-term chain complex. Differential is just the de Rham differential. And the bracket, now I need to define a bracket. So a bracket of two terms in degree 0 is just given here. So you take the ordinary bracket of vector fields, and then you take this double contraction with our three form chi to be the one form, and the bracket of forms of terms of mixed degree. So you could also bracket with an element in degree 0 with an element in degree 1. This is just defined to be 0 in this case. And then this Jacobiator is going to be this sort of triple contraction. So if you have three of these pairs U I alpha I, then I need to give you an element in V1, if you like. So smooth function, and that's the smooth function there. So this bracket does not satisfy the Jacobi identity, and that is the failure there. Okay, so our next example also has input a closed three form. This one's due to, I believe, Reutenberg and Weinstein. And it's, so we'll call it the twisted Courant Lie-2 algebra. So here is the the two-term chain complex. So in degree 1, it's the same thing, smooth functions on M. And now in degree 0, we have just all vector fields and one forms. So if you like, sections of the generalized tangent bundle. And so what we're really doing here, though we're not going to sort of get into the details, but for those who know, we're looking at sections of the Courant algebroid. So this is sort of an important vector bundle, if you like, over M. And so if you're familiar with that, you'll see the bracket and so on showing up here in the when we go over the brackets. So the differential again is also just the Durand differential. And so here's the bracket. If you might recognize this if you know the bracket on the Courant algebroid. This here, this pairing between vector fields in one forms is sort of a standard pairing. So this one is the one with the minus sign, and this time in mixed degree we do have a bracket, a non-zero bracket, and again we have a Jacobiator different from the previous example, and again we're using this notation with the pairing. Okay, so I know I'm just kind of flashing a bunch of formulas at you, but just to maybe sort of summarize or recall that to a closed 3 form on a manifold, we can associate sort of two, say, classic Lie 2 algebras, as we just summarized. Okay. All right. So for the next example of a Lie 2 algebra, we need to recall a little bit. So what's happening? Oh, there we go. We need to call a little bit terminology from Lie groupoids. So if you have a Lie groupoid G, then a multiplicative vector field is sort of like the groupoid version of a vector field. So it's a functor now from the groupoid to the tangent groupoid, and that function is sort of like a section of the projection from the tangent groupoid pi G to G. And if you think about what this boils down to, well, this boils down to a pair of sections. So a vector field on the object space, a vector field on the arrows. And because it's a functor, it has to be compatible with all the structure maps. So, so for instance, x1 pushes, so if you push forward x1 by the source map, you get x0, and sort of similarly for all of the structure maps involved. Okay. So a pair of compatible vector fields, if you like, is one way to think about it. And in fact, so Dan and Eugene Lerman have shown that multiplicative vectors on a Lie 2 algebra, multiplicative vector fields on a Lie groupoid form a Lie 2 algebra. Okay, so the perspective taken there is a tiny bit different, but we can phrase it in terms of the two-term chain complexes. So here it is. So the object space, or in degree 0, what we've got is the multiplicative vector fields, and in degree 1, we're looking at sections of the Lie algebroid of the groupoid. Okay, so if you're unfamiliar with that, then there's just an analog for Lie groupoids analog of Lie algebras for Lie groupoids, namely the algebroids, and if you like, the definition is you take the kernel of ds, where S is the source map, and then just restrict to the unit space. This is some vector bundle over G0, okay, over the unit space. Okay, so that's the two-term chain complex, and then I need to tell you what the differential is. So the differential will be you take your section A and just push it forward by the target. This is the anchor map of the Lie algebroid, and then you sum together these two vector fields, say what are known as the right and left invariant vector fields on the Lie groupoids. This is, say, completely analogous to right and left invariant vector fields on Lie groups. Okay. And the bracket is just inherited from brackets of vector fields. So if we take the bracket of two multiplicative vector fields, sort of just do it pointwise, And then there's a little bit of work to show that if you take the bracket of a multiplicative vector field, so the x1, the vector field on the arrow space, with the right invariant vector field, that this guy, when restricted to the unit space, actually is a section of the Lie algebroid. So you get this bracket of terms in mixed degree as well. Okay, and well, and you could probably guess, because we have the bracket just coming from the Lie bracket of vector fields, then the Jacobiator, of course, is just going to be 0. All right, so one more example of Lie2 algebras to show you. It's an example, I guess, or maybe kind of a sub-example of this one. So as you know, we had started talking about bundle gerbes, which were ultimately some groupoid over X. And so if we start with a bundle gerbe here with connection and curving, then we would like to, well, we'd like to say first, so of course we can just define a Lie2 algebra of multiplicative vector fields on P. But what we'd like to do is now look at those multiplicative vector fields that preserve the connection and preserve the curving. And so here, it turns out to be a little too restrictive to ask the vector field, say, y, to preserve gamma, the connection on the nose, but rather we want it to be sort of delta exact, okay, where delta is this simplicial differential, if you like, just source pullback minus target pullback. So it's for some one form alpha, and similarly, a multiplicative vector field preserves the curving as well. So it preserves both of them if, in addition, again, X doesn't preserve B on the nose, but it's just exact. So it's just D alpha. So one way to, one way to think of this maybe is that, so if you look at the Lie derivative of the pair XY on gamma B, then this thing is exact in the sort of total complex of the double, sort of the natural double complex, if you're familiar with those things, of the simplicial manifold associated to the Lie groupoid P. Okay, so when you look at these multiplicative vector fields, it turns out they those that preserve gamma, or those that preserve both gamma and B, so connection preserving or connection and curving preserving vector fields, they form a Lie2 algebra. And so so let's just quickly see how this works. So I need to give you a two-term chain complex, and so here it is. So in degree 1, it's still just going to be sections of the Lie algebroid. While in degree 0, we will take the multiplicative vector fields, and we'll also throw in the alpha that kind of witnesses the preservation of the connection. Okay, so the vector fields, they preserve gamma, and then you throw in the alpha as well. Now there's a differential we can define. So of course, on the multiplicative vector field component, it's just the same differential that we talked about for just in general for Lie groupoids. But it turns out that any section of the Lie algebroid here does preserve the connection. And just one comment, notice that the alpha here that you get, the one form, it sort of as written depends on a choice of curving, but it turns out that it does not. So you could choose a different curving for the same gamma and get the exact same alpha there. All right, and there's the formula for the brackets. So the brackets are say a pretty natural bracket that you would define, and again, the bracket of terms of mixed degree is just the same one inherited from the Lie2 algebra associated to the Lie groupoid P of multiplicative vector fields. All right, and it's probably easy to see, or at least yeah, it's sort of straightforward to see, say, that the Jacobiator in this case would be 0. So that was for just connection preserving multiplicative vector fields. If, of course, you wanted to look at multiplicative vector fields that preserve both the connection and the curving, well, it's exactly the same, but you just throw in that extra condition, of course, and you get lead to subalgebra of this guy here. All right, so we talked about bundled gerbes and lead to algebras, and now we'd like to just turn to some applications, I suppose. These various lead to algebras and bundled gerbes kind of interact in the context of two-plectic geometry. Okay, so the first thing maybe is kind of elementary, I guess. So recall, so as to motivate the discussion, recall that for principal S1 bundles, a connection form gamma gives you a way to lift vector fields on the base to vector fields on the total space, right? So you could get this sort of horizontal lift of vector fields, and that comes from the data of the connection. But of course, this lift need not be a Lie algebra homomorphism. It need not preserve brackets unless the curvature of the connection is 0. So that's one way to sort of say that or give an interpretation of what the curvature is, right? The curvature of this connection, gamma is the failure of the horizontal lift to preserve the brackets. So it's not a Lie algebra homomorphism, unless the curvature is 0. So this is sort of similar story for bundled gerbes and connection data. So let's sort of see how that goes. So suppose we have a bundled gerbe with connection. Then is this connection, remember, after all, it is a connection form on P. So we can construct a horizontal lift now from multiplicative vector fields on this submersion groupoid to multiplicative vector fields on P. Now, I suppose I could have mentioned this earlier. The multiplicative vector field, so this submersion groupoid, in fact, I think the previous talk kind of alluded to this. This submersion groupoid is equivalent to just the manifold M. And so maybe it's not too surprising that these multiplicative vector fields on X here, this submersion groupoid, are equivalent to, or if you like, quasi-isomorphic to vector fields on M. So you can kind of think of this as vector fields on M in a way. So you get this horizontal lift to the groupoid to multiplicative vector fields. And now we don't expect the horizontal lift to preserve brackets in general, but now we have this extra data perhaps of a curving that can maybe do the trick. So you can use the two form B, the curving, to now define a chain homotopy that measures the failure of this horizontal lift to preserve brackets. And recall that so just by this formula here, by the way, this d by d theta, that's just the generating vector field for the S1 action on P. And so recall our morphisms of Lie 2 algebras were set up so that you have you have your chain map as well as your chain homotopy that measures failure to preserve brackets. And so one might suspect that okay, the data of the horizontal lift and the curving kind of combine to give you a Lie 2 algebra homomorphism, but this is not the case unless your 3 curvature is 0. So the issue here is that the chain homotopy and the chain map, in this case the horizontal lift, they have to be it has to be that sort of coherence condition or the compatibility condition with all the rest of the structure, and that's boils down to this condition with the 3 curvature, the 3 form chi. Okay, so the 3 curvature then can be interpreted as the obstruction to horizontal lift being a Lie 2 algebra morphism. So I should say, by the way, that this result, I think, essentially appeared in the PhD thesis of Braxton Collier. And although in that paper, or in that subsequent paper, I guess, but in that thesis, the perspective is a little different. So here we're using bundled gerbes, and in Collier's perspective, it's very much a sort of stacky perspective. All right. So for the next. Well, maybe I'll just back up a tiny bit. So one of the things that I'm trying to, I guess, impress here is that these bundle gerbes and well, actually, is that multiplicative vector fields are really sort of intuitive tool to be able to model the symmetries of bundle gerbes, right? So, so what we'd like to do now is talk about, so this a next result, but this is one again that involves symmetries of bundle gerbes in a sort of intimate way. So this next result is a result of Rogers here. So if you have a closed 3 form on a manifold, then it turns out that there's an embedding of Lie-2 algebras of the first 2 examples that we discussed. So recall the 2 Lie-2 algebras in degree 0, it was sort of clear that one sits inside the other. There was, remember, one forms in vector fields satisfying a certain condition on the left side and then no condition on the right side. And in degree 1, they had the same, they were both smooth functions on M. So sort of a natural map from one to the other, but of course the brackets and the Jacobiator and everything else were sort of completely different. And so to say that there's an embedding of Lie-2 algebras here really means that there's kind of a chain homotopy that's going to kind of relate the 2 brackets together, right? Or sort of deform one bracket to another. And so that was sort of an important result that there is an embedding of Lie-2 algebras here. So what we'd like to do now is interpret this using multiplicative vector fields. So suppose that you have a bundle gerbe with connection and curving, and chi is its 3 curvature. So then there exist invertible butterflies E and F that make the following diagram to commute. So it turns out that this Lie-2 algebra of observables is quasi-isomorphic to the multiplicative vector fields that preserve both the connection and the curving. And similarly, this Courant Lie-2 algebra is quasi-isomorphic to those multiplicative vector fields that preserve only the connection. And that these quasi-isomorphisms are compatible with Rogers embedding, okay? So we can kind of view that embedding as the natural inclusion of the Lie-2 algebras of multiplicative vector fields preserving both connection and curving into the, well, same thing, but not necessarily preserving the curving. So just a couple of remarks about this this result. So maybe the first thing is that the results in similar, this result and one similar to it sort of appear elsewhere. So I've already mentioned Collier's thesis. And again, there the perspective isn't one of bundle gerbes, but it's sort of a little more stacky and I guess more centered around that example that we gave with the good cover on a manifold. And in the sort of higher, in the enplectic case, so for higher degree forms, this result, well, if the quasi-isomorphism E, it appears in work by Fiorenza, Rogers, and Schreiber. There, the context again is kind of it's sort of at the same time a generalization and also again only working with the essentially the good cover or Czech version of bundle gerbes. And then also there's sort of a similar result in a recent paper by Silvestre and Wurzbacher. In any case, though, we can view this quasi-isomorphism as a kind of generalized prequantization map. So generalized just because it's a butterfly and not an honest map. And prequantization here because if you sort of think of the analogous thing one degree lower, well, this would be like the Lie algebra of observables on a symplectic manifold, and then this guy on the bottom would be like the vector fields on a principal S1 bundle whose curvature was the symplectic form. And so so this would be kind of a prequantization map in that context. And so this is like a higher version of that. And I guess maybe just a quick comment that if you, if you're bothered by the generalized notion of map and you prefer to see an honest Lie-2 algebra morphism, well, you can choose a connection on your submersion, and sort of use the horizontal lift there to get an honest morphism, either for E or for F. So sort of like if you want to choose a little bit of extra starting data, then you can replace your butterfly with an actual morphism that turns out to be quasi-isomorphism because E was. And I guess the last thing I'll talk to you guys about today is that all this behaves roughly well with respect to these gauge transformations that I talked about a while back. So this is where we kind of change the three curvature by an exact form d tau, where tau is the two form on M, and of course the resulting change in the bundle gerbe would be a change to the curving. So let's just see how this goes here. So again, suppose you have a bundle gerbe with connection and curving. So just a bundle gerbe with connection, and its three curvature is chi. And suppose we have a tau, a two-form tau, then there's a natural map between the Courant, the twisted Courant Lie-2 algebras. Namely, you just shift your one form by contraction with tau, and this turns out to be a Lie-2 algebra isomorphism. Okay, and we had given quasi-isomorphisms from the Lie-2 algebra of multiplicative vector fields that preserve the connection. And this quasi-isomorphism turns out to be, so this butterfly turns out to be compatible with this, this gauge transformation tau, determined by tau. Okay, so we might ask, what about E? So what about this prequantization? How does it behave under gauge transformation? And the answer there is a little more delicate in that I don't believe one expects these two Lie-2 algebras to be quasi-isomorphic necessarily. I mean, you can use the prequantization map to kind of map both of them into this Lie-2 algebras of connection preserving multiplicative vector fields, but there's kind of no way to compare them. However, I mean, in general, however, recent paper by Miti and Zambon has an interesting idea to kind of restrict to finite dimensional sub-Lie algebras that using a moment map. So let's just sort of say how that goes. And they give the argument there for the symplectic case, and then go on to show some nice results in the more general context of n-plectic geometry. But if you specialize to n equals 2, you can take their argument actually and just adapt it for the two-plectic case as well. So here goes that. So suppose you have a connected Lie group G acting on your manifold with the three form, and suppose that it preserves the three form, and that this action admits a homotopy moment map. So in particular, this just means a morphism of Lie-2 algebras where we view the Lie algebra G of the group G as just being concentrated in degree 0. So if you now take your two-form tau, your invariant two-form tau, and you can shift the two-plectic form, or you shift the three form by this exact d tau, then it's not too hard to cook up then a new moment map for this new three form, right? So you've changed the three form, and so now your moment map condition is sort of say what it means to be Hamiltonian as a vector field changes, but you know how much it changes by, so you can adjust the moment map if you like and get a new one. And so it turns out this diagram commutes. In other words, that if you map each of these two Lie-2 algebras into connection preserving multiplicative vector fields, well, you can look back at the Lie algebra and just precompose with the moment maps, and these two guys are the same. Well, they're two isomorphic. Okay, so this this prequantization map E is sort of as good as we think it might be for with respect to compatibility with gauge transformations or shifting by this form tau. Okay, so I think that's it for me. I'll stop there. Thanks very much for your attention.
Okay, let's thank the speaker. So any questions? Yeah. Okay, so I think if there's no more questions, let's thank the speaker again. Then let's take a break. And the next talk will be